All right, so we're looking at section 2 of chapter 5, and this is going to get a little more into the defining and the explanation of definite integrals. Oh, by the way, this guy here is the other guy who is credited with coming up with calculus, Gottfried Wilhelm Leibniz, and it was this guy and Isaac Newton. He actually, this guy, Leibniz, came out with his writing before Newton did, and Newton came back later. I mean, we're talking not like a week later, we're talking years, about 2 years later, and released his writings on what he'd found, and said, no, I did it first. And then that actually sparked a battle between these two guys. And of course, Isaac Newton, he was still famous. He was actually already famous at the time. So he actually ruined this guy. This guy ended up dying pretty much penniless. And I know some of you guys are thinking, well, that's what he gets for coming up with calculus. But actually, calculus is a great thing. All right, so when we find the area under a curve by adding rectangles, the answer is called a Riemann sum. The width of a rectangle is called the subinterval, or the length of the subinterval. And the entire interval we're going to call the partition. We've also been calling it the interval, but just to kind of not get confused with subinterval and interval, we're going to call the entire length the partition. Now, the subintervals, while we've looked at all of them and actually have calculated all of them to be the same size, subintervals do not have to be the same size. They actually can be different sizes, and you're going to run into that a lot of times when you do these Riemann sums on information that comes from tables. The length between 1 and 3 are your first element and your second element in your table may not be the same distance from your second element and your third element. You may have a table where when you're looking at the table, you may have a 1 here, a 3 here, a 7 here, and a 9 here. Or you got a difference of 2 here, and a difference of 4 there, and a difference of 2 there. You could even make this 10, and you've got one difference of 2, difference of 4, and difference of 3. So in this case, the width of the partition, or the subintervals, would be 2 here, 4 there, and 3 there. So the width of the subinterval would not be the same. But that's not a big issue. We can still do our approximations by that using subintervals that are not the same size. If we do that, though, we've got to remember that we're going to multiply by the width of the subinterval each time. We can't wait till the end and multiply by one time because, well, it's not common for all of them. All right, now if the partition, the whole thing, is denoted by P, then the length of the longest subinterval is called the norm of P and is denoted by this thing right here, which is essentially looks like double absolute value of P. That's actually not, it's just the notation, and that notation means the norm of P, or the longest subinterval. Now, as the norm of P gets smaller, then the approximation for the number gets better. Now, I want you to think about this for a second. Don't get confused. Remember, the norm of P is the longest subinterval. So if the longest subinterval gets smaller, what does that mean about all the other subintervals? Well, that means they have to get smaller too. And if all the subintervals get smaller over a given partition, what does that mean? That means we have to have more subintervals to cover the partition. And what did we find in the last section when we had more rectangles? The more rectangles, the more accurate our approximation. Same idea, we're just discussing it a little differently, and we're doing this for a reason. Now, the area, don't freak out over this. I'm going to walk you through this. The area is the limit as the norm of P approaches 0. That's the longest subinterval approaching 0. That means all the other ones are approaching 0 as well. And then this thing right here means sum. It's sigma notation. And we're doing k equals 1 to n. That just means we're going to number off each subinterval. And f of c sub k is multiplied by delta x sub k if p is a partition of the interval from a to b. Now, before you freak out and say, I don't understand anything about what this is saying, remember, how did we find the area of each one of our rectangles before? Well, we calculated the height. Like here, it's notated as, this shows that we're doing a midpoint. So we found the height of this. Well, what was that? That was f at some c. That's where this comes from. So that is the height. And then what is delta x sub k? Well, the change in x just means the width of the subinterval. That is your delta x, whatever it may be. Your delta x, the reason they do the subscripts is the c for the first subinterval is not going to be the same c as the second subinterval and the third subinterval and the second and the fourth subinterval. Same thing with your delta x. If these things are not equal, then the width of the subinterval may not be the same for the first subinterval, second subinterval, third subinterval. That's why we have to do our subscript to determine which one we're actually talking about. So all this is adding up the areas of the rectangles. That's what this is. The height times width is the area of the rectangle. And then this means we're adding them up. And this means if the norm of P is approaching 0, that means we have infinitely many rectangles that we're adding up to get the area. That's all we're doing. So the limit as the norm approaches 0 means we're doing an infinite amount of rectangles. The sigma says we're adding all the areas of all those rectangles up, and that's what this part right here is calculating each individual rectangle. All right, now this ugly thing right here is called the definite integral of f over the closed interval from a to b. Now, before you have a conniption and decide it's time for you to drop calculus, you need to understand this is not the notation we're going to use. We are walking our way through the complex stuff to get to the application and the symbology that we're going to actually use. So don't freak out over this. Just understand kind of a general idea of where it's coming from and what this means. Now, if we use subintervals of equal length, then the length of a subinterval is just delta x, which is b minus a over n, which means that right here we could use not the subinterval or not the subscript. We wouldn't have to use it if all the subintervals were the same. So our definite integral then will be given by the limit as n approaches infinity. N is the number of rectangles, by the way, the number of subintervals we're breaking it into. That's just another way, and it gets rid of our norm. We don't have to worry about the norm because now all of our subintervals are the same. We can identify just one of them as all of them because they're all the same width. But we're going to let the number of rectangles approach infinity, and we're going to add the area, height times width, of all these rectangles up. And that's going to be our definite integral. All right, now Leibniz introduced a simpler notation for the definite integral. He said that this limit thing here that we were just been writing down can actually be expressed as this little squiggly thing here from a to b of f of x dx. This is the notation he came up with. Now, Newton came up with some notation as well, but it was not all that cool. It was a lot harder to deal with. This is what we use here. All right, and all this says is we're going to do the antiderivative, or the integral, from a to b of f of x dx. Now, notice here that our delta x, remember we talked about this back when we were talking about derivatives, our delta x, or a change in x, becomes dx when that change becomes very, very, very small. And that's what we're talking about when we're talking about the number of rectangles going to infinity. So this is a super, super, super tiny change in x. Now, what all this stuff is, we're about to list it. This is the integration symbol, and that kind of looks like an S, doesn't it? Well, that's actually a Roman-ish S. So anytime you see that, you need to think the same thing you think of when you're thinking, or when you see the sigma notation. This means add. Guess what? So does this. You're summing things. You're adding up stuff. Both of those are the same thing. So you need to think of them. They're very, very similar. They're not exactly the same thing, but they're very similar. So you need to think of them as the same thing. They should relate the same thing in your head. All right, and then we have these two numbers, which are the lower and the upper limit of integration. What that means is you're finding, this thing says that you're finding the area under the curve, and you're finding it from A to B. Now, what curve are you finding the area under? Well, that's what this is right here. So f of x is your integrand. That's the thing you're taking the integral of. And then the dx over here is the variable of integration. It tells you what you are actually integrating this with respect to. Now, primarily, all of our integrals are going to be dx or dy or dt. One only. As we talked about earlier, when you get into Cal 3, if you take Cal 3, you're going to get into multivariable calculus, where you're actually going to take an integral of x, or with respect to x, then with respect to y, then with respect to z, and it's telling you how everything's changing in all those different directions. So right now we're only dealing with one at a time, but you can actually do integration with more than one, with respect to more than one variable. All right, so we have the notation for integration, but we still need to learn how to evaluate the integral. Now, in section 5.1, we considered an object moving at a constant rate of 3 feet per second. And since rate times time was distance, 3t equals d, etc., etc. And if we drew the graph, so, I mean, this is straight from section 5.1, so don't worry about copying this again. If the velocity varied, we found that it would be the area under the curve, but, and here the area under the curve, if it's a linear, well, this is really easy. That's just a trapezoid. So we can find the area of this trapezoid with 1/2 base 1 plus base 2, 3 plus 1, times the height, the distance between the bases, which is going to be 4, and that gives you 8. Now, notice right here, we had the velocity, and we actually did something to go from here to make this thing kind of weird. Well, think about this. If we took the derivative of this, what will we get? Well, the 2 would come out front. We'd end up with 2 over 4, which would be 1/2 t. Oh, look at there, 1/2 t. And then the derivative of t would be 1. So we actually just took an antiderivative there. So 1/2 t plus 1, its antiderivative would be 1/4 t squared plus t. And then if we plug in 4 to that, 1/4 of 4 squared plus 4 gives you 8. So the same thing. So we just found the area under this curve. Two different ways. But notice here that the area is a trapezoid, so if you've got a nice linear equation, it may be easier, instead of doing the calculus, just to find the area under the curve using some of our geometric figures. Now, what if v equals 1/8 t squared plus 1? Well, we could split the area under the curve into a lot of thin trapezoids, and each trapezoid will behave like the large one in the previous example. Now, you're looking at this, I know, and you're thinking, well, that's pretty dang accurate, so that may be an exact answer. It's actually not. If you zoom really, really close, if you could zoom really, really close in, you're going to see that you've got a curve for the function, but you have a line for your actual trapezoid part. So it's not going to be exact, but it is going to be a much better approximation than anything we've dealt with in the past. Now, it seems reasonable that the distance will equal the area under the curve the same way it has in every other problem we've dealt with. So if velocity is ds dt, which is 1/8 t squared plus 1, we can do the same thing we were just doing here, and we can take the antiderivative of that. And if we do that, we're going to get 1/24 t cubed. Now, what we do here is this. Power rule in reverse. Before, when we took a derivative, we would take this power, move it out front and multiply it, and then we would subtract 1. Well, do the exact opposite to that. You're going to add 1 to your power, so 2 plus 1, and instead of multiplying out in front, you're going to divide the whole thing by that new number. So we end up with t cubed times 1/3, and 1/3 times 1/8 gives us 1/24. Right? Same thing over here. This is actually t to the 0 power. You can think about it that way. So if we add 1, we're going to get t to the first power, and then 1 moves out front, and we divide by it, and 1/1 t, sorry, 1/1 times t is just going to be t. So this is our antiderivative. This is what s is. So if we plug in 4, we're going to get 1/24 4 to the 3rd power plus 4. 4 to the 3rd power is 64. 64 divided by 24 plus 4 gives us 6 2/3. Now, if you'll remember, we actually worked with this problem right here specifically over the interval from 0 to 4 in the last section, and I told you that it was 6 2/3, or 6.6 repeating. So the area under the curve is 6 2/3. So we can use antiderivatives to find the area under a curve. All right, let's look at it another way. Now, you need to kind of follow this. You don't necessarily, you're never going to have to replicate this operation again, but writing this down is important, and I want you to kind of follow along with what goes on. All right, let's let a sub a of x equal the area under the curve from a to x, and a is a constant. X is not. All right, so a sub a of x, this subscript and this thing in here are simply telling you the beginning and the ending part. Don't get tied up in the notation. Just understand you're talking about the area from a to x. That's this notation. All right, and that's the area that's shaded right here now. Now, we know that a sub a of x, or the area from a to x, plus the area from x to x plus h is going to equal the area from a to x plus h. We can see that right here. The area that's blue plus the area here that's not shaded but enclosed. If we added those two together, we're going to get the area from a to x plus h. That's all this little statement right here says. Now, we can then go in here and we can do some moving around. We can actually go in and we can move the a sub a of x to the other side by subtracting. So if we actually go and subtract this area from both sides, we're going to say that the area from x to x plus h is equal to the entire area from a to x plus h minus the area from a to x. So we've got this whole area here, and we take this part out, and what do we have left? Well, we have the unshaded part here. Everybody following so far? Just look at the little pieces. Remember, this is where our area starts. This is where the area ends, going left to right. Now, the area of a rectangle drawn under the curve would be less than the actual area under the curve. We know that. That's our inscribed rectangle right there. And that would be an underestimate. So we know that at that point it would be less than. If we then went in and did an inscribed or a circumscribed rectangle, that's going to be one that's going to be greater than. And the area of a rectangle drawn above the curve would be more than the actual area under the curve. So we've got max f, maximum height, minimum height and maximum height to get our two rectangles over this interval from x to x plus h. So we know that the short angle is going to be less than or equal to the actual area under the curve, which is going to be less than or equal to the tall rectangle. So when we put everything in, what is the area of the short rectangle? The area of the short rectangle is going to be the minimum value for f times h. And the area under the rectangle is what we calculated on the last page, a sub a of x plus h minus a sub a of x. And then that's going to be less than the area of the tall rectangle, which is h times the maximum value of f, the maximum value of the function over this interval. By the way, that's what those are. The minimum value of f is just the minimum value over this little subinterval that we're talking about for that function. And our maximum f is the highest value over that interval. Right? So then we can actually divide everything through here by h, and we're going to get the minimum of f is less than or equal to a sub a of x plus h minus a sub a of x all over h is less than or equal to the maximum value of f. Now, hopefully, this thing right here looks a little familiar. That looks very, very much like part of what we had with our difference quotient, right? That actually looks like the difference quotient. Well, what did we do with the difference quotient? We took a limit. So as h gets smaller and smaller and smaller, the minimum value of f and the maximum value of f are going to get closer together. Because remember, what is h? H is the difference of the distance from x to x plus h. One x value to the other. So if we let h get smaller, what's going to happen to those 2 points? They're going to get closer together. And if the x values get closer together, then the minimum value and the maximum value for f are going to get closer together as well. So if we take the limit of this thing in the middle, right here, the limit of a of x plus h minus the a sub a of x all over h equals f of x by the squeeze theorem here, by the sandwich theorem here. If we let h get smaller and smaller and smaller, these two values are going to get closer together until they are the same value. That means that they squeeze this thing down. Well, if the minimum value of f and the maximum value of f are the same thing, it's just f of whatever value or whatever x value we're at. That's why this works. Well, this over here is actually looking like it's a derivative. It is the derivative, the definition of the derivative of a sub a. So the derivative of a sub a of x equals f of x. Now what we want to do here is we're actually going to take the antiderivative now. That's going to undo this part over here. And it's going to take the antiderivative of f of x, which is going to be denoted by a capital f of x. When you use a capital letter, that is typically going to represent the antiderivative of the lowercase letter. So capital F of x is the antiderivative of the lowercase of x, of f of x. Now the plus c we'll talk about later. Just trust me on the plus c for now. And we're going to end up solving for that plus c. But that plus c is going to make more sense in just a little bit. So a sub a of x is equal to the antiderivative of f of x plus c. Well, if we were to take the initial value and go the area from a to a, well, the area, if it starts and ends at the same place, we know this thing's going to be 0. So that has to be 0, and it equals f of a plus c. Which means what? It means that f of a, or negative f of a, equals c. So if we take this part right here and plug it back in right here for our c, we know that the area from a to x is equal to f of x minus f of a. So area from a to x is the antiderivative of x minus the antiderivative evaluated at a, and that's going to give you what the area from a to x is. So the area under the curve from a to x is equal to the antiderivative at x minus the antiderivative at a. That is a huge, huge, huge concept. That's actually the first part of what's called the fundamental theorem of calculus. All right, so to kind of tell where we've been and where we've gotten to, we started off with the area equaling this big ugly thing here. And then it equaled this thing. And then what we just found is we found how to evaluate this thing. That's what we just proved. We proved that if we want to find the integral from a to b of f of x dx, we want to take the antiderivative of f, plug in b, and subtract the antiderivative of f, and we're plugging in a. That's actually how we evaluate this antiderivative, or this definite integral. That's what this is called. It's definite because we have endpoints. Indefinite means we would not have the endpoints. But the integral, or the integral from a to b of f of x dx is found by taking the antiderivative of f, plugging in b, and subtracting the antiderivative of f when we plug in a. All right, so let's do an example here. We've got y equals x squared, and we want to find the area under the curve from x equals 1 to x equals 2. Well, to find that area, we're going to do an integral. We're going to go from 1 to 2, and we're doing x squared dx. So first thing you want to do is you want to do the antiderivative of x squared. Well, remember the power rule. We're going to add 1 to 2 and then divide by that. So we're going to end up with 1/3 x cubed. And we're going to evaluate that from 1 to 2. And don't worry so much about the notation right now. We'll talk about it and I'll explain it later. Just write it down now. That means we're evaluating it from 1 to 2. So that means we're going to plug in the 2 value. So what is 2 cubed? Well, it's 8. And 8 times 1/3 gives us 8/3. And we're going to subtract when we plug in our lower bound. We plug in 1 there. We're going to get 1 cubed, which is 1 times 1/3 gives us 1/3. So 8/3 minus 1/3 is going to give us 7/3. So that is this area right here. The value of that area right there is 7/3 of whatever units our axes are in. All right, now let's do the exact same problem on the TI-89. Let me show you how. It's not real difficult, but you can practice it when you get into class sometime or mess around with a calculator. It's important to know how to do these. And if you have questions on how to do it on the 84, just ask me and I'll show you. It's not real difficult. It's very similar to what we did with the derivatives. Here's how you put it in. The 2nd and 7 button gives you a little squiggly thing. And then all you do is you put in your function that you're integrating, comma, what you're integrating with respect to, the variable that is, and then comma, lower bound, comma, upper bound. Now guys, you've got to get these in correct order, because if you did 2 comma 1, you're actually doing it backwards, or you're doing it backwards the way we would normally do it, and you're actually going to end up getting a negative 7/3. That's something we'll talk about later as far as applications, but you always do lower bound, upper bound, the exact order that you want to do, and then hit enter and it'll give you the answer. All right, so here's an example. Find the area between the x-axis and the curve y equals cosine x from x equals 0 to x equals 3/2. Now this one's a little different. We're looking at for the area. Area is always going to be positive. If we were looking for the function value, let's say f of x here equals cosine x, and we wanted to define the integral of f of x over this, it would be a little different. But when they specifically say find the area, you know it's got to always be positive. And this over here, because of the negative number for the height here, this is going to end up being negative if we do not correct it. Now we're going to do this both with a calculator and by hand. We're going to do by hand first. So we've got to take this part over here and make it positive. So we're going to end up doing the absolute value thing, or since we already know that all this from pi over 2 to 3 pi over 2 is going to be negative, I'm just going to throw a negative out in front of it. So here's what I'm going to do. I'm going to split it up into parts. I'm going to go from 0 to pi over 2 of cosine x dx, and then I've got the other part over here, the integral from pi over 2 to 3 pi over 2 of cosine x dx. And because I know that's negative and I want to add that as a positive, I'm actually going to go ahead and do subtraction. Because remember, if this value is going to be negative and I subtract a negative, it's the same thing as adding a positive. So I'm essentially taking care and making an absolute value out of this with that negative right there. I'm doing exactly what an absolute value would do. I'm making it positive. All right, so back to thinking about trig functions here. We know that when we take derivatives, we've got sine x, cosine x, negative sine x, negative cosine x, and then it wraps back around. We're taking the derivative there as we go in that direction. Well, if we're taking the antiderivative, we're just going against our arrows. So if I'm taking the antiderivative of cosine x, I'm going against the arrow, and it's going to be sine x. So this is going to be sine x evaluated from 0 to pi over 2 minus sine x evaluated from pi over 2 to 3 pi over 2. So then, of course, I can just plug things in and find it. So for this first one here, I'm going to have the sine of pi over 2, upper bound, minus the sine of 0, lower bound, minus, over here, the sine of 3 pi over 2, upper bound, minus the sine of pi over 2, lower bound. Now, knowing your trig functions and for those key values are going to be really, really important, because this would be a no calculator question. It could very easily be a no calculator question. The sine of pi over 2, of course, is 1. Sine of 0 is 0. So we end up with 1 minus 0. And then sine of 3 pi over 2 is negative 1 minus the sine of pi over 2, which we already know is 1. So we end up with 1 minus negative 2. Subtracting a negative is like adding a positive, so we end up with 1 plus 2, which gives us 3. All right, so that's how you would do it if we were looking for the area. Now, guys, if we were looking for just the function value like we were talking about earlier, if we were evaluating f of x over this interval, there is nothing there, if we don't talk about area, that says this has to be taken the absolute value of. So this ends up being the positive value, this ends up being the negative value, and we end up with 1 plus negative 2, which gives us a negative 1. We're going to talk more about the difference in those two things, but just understand that that is the case here. But because of the word area, we have to do the absolute value and change everything that's negative into a positive. Now, how in the world will we do this with a calculator? Well, here's how we would do it with a calculator. We're actually going to use absolute value. We're going to integrate this thing the same way we would before with the squiggly, the second 7. But we're going to go to catalog and choose absolute value and then put cosine x in the absolute value. And then our integral from 0 to 3 pi over 2. But we've got to remember to put in the x here to tell what we're integrating with respect to. So while it'll look like, while you'll type it in like this, when you actually hit enter, it's going to show you absolute value of cosine x in your integral. So 0, 3 pi over 2 dx. If it does not show you this exactly the same way, you've put something in wrong. And then it will still give you 3. So always check that pretty print thing to make sure that it's looking exactly like it should. And the absolute value, once again, takes care of the negative part and makes it positive. So if you use the absolute value function, you don't need to find the zeros to break it up into parts. If you're doing it by hand, though, you have to find where it crosses the x-axis so you know what parts are going to be negative in front of them, or what parts you're going to have to subtract because they're negative, and what parts are okay with just adding because they're positive. All right, so here's a couple of questions. If the integral from a to b of f of x dx is greater than 0, then f of x is positive for all x in the integral from a to b. True or false? Well, what that means is if the area is greater than 0, or the area under the between the curve and the x-axis is greater than 0, then f of x is positive. Does f of x have to be positive for this integral value to be 0? Or to be greater than 0? Well, no. And this case right here is a good example to look at. In this case, it could be negative because more of it is actually below the x-axis. But what happens if this thing's flipped? What if we had this? What do we notice that's positive here? Ignore this, ignore this. So this part's negative and this part's positive. When we add these together with their actual signs, what do we know? Are we going to end up with a positive or are we going to end up with a negative? Well, we're going to end up with a positive because what? We have more positive value than we have negative value. So in that case, just because your integral is ending up being a positive number, it does not mean your function value was above the x-axis the entire time. So that means that that is a false statement. The fact that our integral is greater than 0 simply means that there was more of the function, or more of the area between the function and the x-axis was above the x-axis than was below the x-axis. That's all that means. All right, so if f of x is positive for all x in the interval from a to b, then the integral from a to b of f of x dx is greater than 0. So this one's kind of flipped the thing over. If the function is positive for all the x, is the integral guaranteed to be greater than 0? Well, yes, it is. Because if we go in here and we have something that's all above the x-axis, then all we're doing is we're adding positive numbers. So that one's true. All right, now if the integral from 2 to 5 of f of x dx equals 18, then the integral from 2 to 5 of f of x plus 4 dx equals what? Now this one you're using some properties. Now properties of integration are very, very similar to the properties we should have learned about limits. That means that we can actually split this thing up. This can be rewritten as the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of 4 dx. Now, what do we know about this part right here? Well, that part right there we were told was 18. So that means we end up with 18 plus, I'm just going to write this part again before we actually start solving it. So 18 plus the integral from 2 to 5 of 4 dx. Well, remember, to find this, we're going to do what? Take the antiderivative of 4, which is going to be 4t. We've got 18 plus 4x, sorry, not t, evaluated from 2 to 5. So the antiderivative of 4 is 4x with respect to x. Then we evaluate that from 2 to 5. So that means we have 18 plus 4 times 5 minus 4 times 2. All right, so that means we have 20 minus 8, which gives us 12, and 18 plus 12 gives me 30, which is E. All right, this one you actually want to think about visually. Try to visualize this thing. Try to graph this thing and then calculate what the area under the curve might be using geometric figures. So what is 4 minus the absolute value of x? Well, to kind of help you along with this, you can rewrite this and think of this as negative absolute value of x plus 4. Now, think about your shifts and your reflections and all that. What does this graph look like? Well, remember, absolute value starts off as the v. What's the negative thing going to do? Well, the negative in front of the x is going to take this thing and it's going to flip it over. So it's going to become the downside's v. And then what happens when you add 4 to it? It's going to shift the whole thing up 4 units. So what you're going to do is you're going to have 1, 2, 3, 4, and you're going to have your downward opening absolute value. Now, since both of these are slopes of 1, if this is 4, this is 4, and this is negative 4. So all you're doing here is what? You're finding the area between this curve or this triangle and the base here. So what is the base of this triangle? Well, the base going from here to here is 8. What's the height of the triangle? Well, the height is up to the highest point, which is going to be 4. So you're ending up with 1/2 base times height, which is going to be 1/2 of 32, which is 16. So if you have situations like that that you can actually sketch out that are going to end up being nice little simple geometric figures, then use those to actually find the area. Remember, all you're doing with an integral is you're finding the area between the curve and the x-axis. That's all you're doing. All right, now if the interval from 0 to pi is divided into n subintervals of length pi over n, and c sub k is chosen for the kth subinterval, which of the following is a Riemann sum? So remember, all we're doing is we're adding all these things up. So we have n subintervals. That means n goes on top, k at the bottom, because that's where all the k is the counter for the subinterval. And then what's the area going to be? Now we're dealing with sine here, it looks like. The sine's in all of ours, so we're actually finding the Riemann sum for sine x over the interval from 0 to pi. So we're looking for how that's going to happen. Well, n subintervals means we're going to take the width of the subinterval and divide it by n. So pi divided by n equals the width of the subinterval. So we've got pi over n right there. And we're going to have the sine of c sub k is going to be what we're doing. There's the height. There's the width. And height times width gives us rectangle. So that's going to give us the area of the rectangle. This means we're going to add up n number of rectangles. So which one's it going to be? Well, it looks like it's going to be C. All right, now which of the following quantities would not be represented by the definite integral 0 to 8 of 70 dt? So all of these are different ways that we could express the number that we found here in terms of something. So which one of these would not? All right, the distance traveled by a train moving at 70 miles per hour for 8 minutes. The volume of ice cream produced by a machine making 70 gallons per hour for 8 hours. The length of a track left by a snail traveling at 70 centimeters per hour for 8 hours. In other words, the goo. That's pretty nasty. The total sales of a company selling $70 of merchandise per hour for 8 hours. The amount the tide has risen 8 hours after low tide if it rises at a rate of 70 millimeters per minute during that period. So which one of these would not be represented by that integral? Well, it's actually a trick question. The thing is, you've got to understand that your units have to line up. There's one of these that the units do not line up on. More specifically, the times don't line up. Here we have miles per hour for 8 minutes. That would not be, if this was in miles per hour in here, then our upper and lower bounds must be in terms of hours. Otherwise, the integral does not work correctly, because this should give us miles, and miles per hour times minutes does not cancel out the hours or the minutes. So you've got to be really careful and make sure that your units are going to line up and do what they're supposed to do. So this one is a trick question, but it is answer A. And all because the hour and minutes are not the same as far as the time is concerned and the measurement. All right, that's all of 5.2. Make note of any questions you have or concerns or anything, and we'll address those first thing in class.